So I don't read too much into a pop quiz. I just, I think it's helpful for you to gauge whether or not you understood what was happening. It's easy enough to believe that you understand what's happening when I do it, but you doing it is a separate thing, right? So, and some of you haven't quite understood the instructions, which is okay. I mean, I'd rather you not understand the instructions on the quiz as opposed to the test, right? So I said set up, but do not determine. What I mean by that is set it up, but don't determine the constants. So like, we do this thing where we set up the form of the particular solution, usually with like big A, B, C, right? And then we plug it in and do algebra to find the values for A, B, C. So if I ask you on the test to set it up, but not determine, I'm specifically saying do not waste your time trying to figure out what the constants A, B, C, and D are. On the other hand, if I just say find the general solution, you very much should spend your time finding the values for A, B, C, and D. And don't trick yourself into thinking that after you write down the template solution, you're done. That always happens. This next test, there's always a student who has got pretty good understanding of the material and tricks themselves into thinking they're done with a problem when all they've done is just set up the particular solution, right? So you actually need to plug it in and work it out if the problem is to find the general solution. But on the other hand, like the problem in the quiz, if it's just to set it up, then I'm sparing you that extra, 4 or 5 minutes of algebra, or whatever, how many minutes it is for you. Depending on the problem, sometimes it's more, right? But anyway, I will post a solution to quiz 7 and quiz 8 here hopefully today, and then you can look at those and we'll go forward from there, okay? Anyway, I'll begin with a word of prayer. Heavenly Father, we thank you for this day. Again, I thank you for the students and this wonderful weather. Help us to glorify you what we do this day, Lord. In your name I pray, Lord Jesus. Amen. So any questions before I dive into it here? Yeah.
This wasn't for the quiz, but this is for the take-home quiz.
Uh-huh.
So when you're solving for like V1 and V2, you have y f dx over a y1 prime blah 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 blah.
Yeah.
What's a?
A is the leading coefficient in the differential equation. So like so goodness gracious. Oh, that was not good. My back almost did something bad there. So we solved this problem. I think I put a F over here. I might have put a G, I don't remember. And so we said that the solution to this is like C1y1 plus C2y2 plus, and then we had, V1y1 plus V2y2. This is the particular solution, and V1 was the integral of minus Fy2. Now it depends on if I use dt, the t is my independent variable, right? Y1, y2 prime minus y2, y1 prime. And V2 is the integral of Fy1 dt over y1, y2 prime minus y2, y1 prime, right? Well, almost right, because the thing you're just asking me about is currently missing from my formulas, perhaps intentionally so. And so that's that A right there, all right? That's the A that we're talking about. It's the same A that appears right here. Oftentimes, A is equal to 1 in problems that I give you, but it doesn't have to be that way. So, other questions? That's a good question. All right. Mm-hmm.
A is just the coefficient.
Yeah, A is the leading coefficient. Now this is only for the, this is for the n equals 2 case. The n equals 3 case I said I wouldn't test you on. So, And in n equals 1 case you've already done. That's the integrating factor method, right? Integrating factor method actually is variation of parameters when you tilt your head and squint and look at it. So today we're doing applications. So there's really only 2 applications to think about, all right, for here. And the one I've tested you on, and the other one I don't test on because it scares people, but I'll talk about it at least in here. So basically, we can talk about spring springs with friction. So let's talk about that. So you've all had Physics 231, so you know that the mass times the acceleration, right, is equal to the net force. Yeah? And we did a little bit of that before with the energy analysis business, right? But in one dimension, so in the one-dimensional context, of course, this can just look like perhaps m, we'll use x for the one dimension, so mx prime prime, right, equals to the net force. Now, so the net force we have in mind, I'll draw a picture over here. You know, we've got some spring, right? And then it's attached to some mass over here, right? And then the whole thing is perhaps immersed in some sort of oil, okay? Something like that. So it's all immersed in some oil, and that oil gives you a friction force, all right? So the forces that are on the mass, on the one hand, depending on whether this is stretched out, like let's suppose that the spring is stretched out. Which direction does the force go? This way, right? So we do minus kx for the spring force, and here I'm assuming that, like, you know, maybe this is where equilibrium position is, x equal to 0. And what's the other force involved here? Gravity doesn't come into play in this problem, all right? Damping. So that if the motion's this way, right? Then the the force of friction would be this way, right? So a formula for that is minus BV, where B is the coefficient of friction. So our net force, that's it for the forces involved. This is the spring force problem. And so what we got here is mx double prime equals to minus kx minus BV. And you can check that that makes sense. Now here, you know, mk, m is mass, k is the spring constant. So that's Hooke's law. It's interesting to note Hooke was a contemporary of Newton, but in Newton's master work, the Principia, he doesn't mention Hooke, which is kind of funny. It would be like somebody writing a book about the Yankees and somehow never mentioning the Mets in like a 1,000-page book or something. I don't know. It would just be, would make sense. Not that I care. But anyway, so but here this is, I don't really have a name for B, but it's the coefficient of I don't even have a name for B, but B is the constant for the friction. The friction. I guess you call it the friction constant. I'm not sure really what its official name is. Of course, this is just one model for you know, velocity-dependent friction. If you've taken Dr. Budera's Physics 231, you probably studied other models of friction and talked about the fact that actually the exponent's a function of velocity itself, so it's much more insidious than this, right? Because it's like quadratic at low velocity, but it gets to be cubic at higher velocities, and really you need a lot of data and numerical methods to do it justice, because the mathematics is formidable for direct closed form solutions. That's not the case here. This is very much amenable to direct closed form solutions. So we'll just call this the friction constant. So mathematically, the key thing to note about all these is that the mass is greater than 0. That's etched in stone. K is greater than 0. That's pretty much, you know. But the B could be greater than or equal to 0, because we'd like to look at with B greater than 0 or without B equals to 0 friction problems. All right? So if we want to make the friction go away, we just make the B equals to 0. Okay, so of course, we can also write this as minus kx minus bx prime, right? So let's rewrite that again. What's the problem we're trying to solve here? We're trying to solve mx prime prime plus bx prime plus kx equals to 0, right? That's the problem we're thinking about. Can we solve this? Yeah, I mean, this is the constant coefficient second order differential equation. We can easily solve this, right? So what we get excuse me, is m lambda squared plus b lambda plus k equals to 0. That's my characteristic equation. And how do you think we should solve that? Well, what I'm going to do is I'm going to divide by mass just to make things like nicer. So I've got lambda squared plus b over m lambda plus k over m equals to 0. And then I'm going to complete the square. So this gives me lambda plus b over 2m, quantity squared, equals to, well, minus k over m plus b squared over 2m squared. So we could rewrite that again as minus 4m k plus b squared divided by 2m squared, I think. Agree, disagree? What do you guys think? So I had to multiply the first one by 4m over 4m, which is 1, to get that. So, and then I get lambda is equal to, minus b over 2m plus or minus the square root of b squared minus 4mk. And maybe I should have left the 2m out, right? Because I'll write it this way. And of course, at this point, you guys are like, well, I wrote down 3 minutes ago because I know the quadratic formula. Why don't you? Well, fine. I'm just deriving the quadratic formula. You got me. Guilty as charged. All right, fine. So what's the situation here? There are 3 cases, right? What are the 3 cases? Maybe 4 cases if you want to cut things more finely. So let's say case number 1 would be that b squared minus 4mk is greater than 0. All right? What happens then? Can you describe it mathematically? We can get we get real numbers. So this has a name. This is called the overdamped case. So we get, I'll call this lambda plus and minus for the obvious reason. All right, lambda plus minus equals to minus b plus or minus the square root of b squared minus 4mk over 2m. As you said, these are real numbers, right? Let me be more specific. What kind of real numbers are they? Since m and b are both positive, can you tell me, in terms of the square root, is the magnitude of the thing inside the square root more or less than b? Look at it. You've got b squared minus a positive thing, right? So this has to be less than b in terms of its magnitude, right? So when you think about adding it to minus b, it's still negative. And when you take minus b minus it, it's negative. These are both negative. That's important. So this is an element of minus infinity to 0, not included. And this is called the underdamped case. or underdamping. So the solution, well, what would the solution look like? X equals to like C1 e to the lambda minus t plus C2 e to the lambda plus t, right? That would be your solution. It's a pair of exponentials. What happens to those exponentials as time goes to infinity? They're both negative values, right? So they're both dying to 0. So the motion goes to 0 for time going to infinity, which makes sense, right? It would be weird if friction somehow made the motion blow up, right? This is one of your homework problems, by the way. Maybe I haven't written it quite this way, but the mathematics I'm doing right now is one of your homework problems. The other case, I might have changed the names. I mean, I might have changed the letters in the problem to protect the identities of the innocent. But let's see here. So b squared minus 4mk equals to 0 is another case, right? The discriminant in the quadratic equation could be 0, right? In that case, we have the double root lambda plus equals to lambda minus equals to simply minus b over 2m, right? And then the solution looks like x equals to c1 e to the minus bt over 2m plus c2t e to the minus bt over 2m, right? Again, I would point out that this is less than 0, right? It's less than 0. Now, you might wonder what happens as time goes to infinity here. You tell me how to analyze this. The limit as t goes to infinity of t e to the minus bt over 2m. What happens there? Let me remind you, we can rewrite that as t divided by e to the t bt over 2m, right? Why am I doing that? I'm doing that to emphasize the fact to you that this is an indeterminate form, right? It has the form of infinity over infinity, as I've rewritten it. So I can apply L'Hopital's rule, right? And L'Hopital's rule tells me that I get what? I get 1 over b over 2m e to the bt over 2m. So as some of you hopefully knew already, this limits to 0, right? Because exponential growth beats polynomial growth, right? So having an exponential with a negative argument will kill any polynomial in front of it in time. So again, we see that this solution, as time goes to infinity, goes to what? It goes to 0, no matter what my choice of C1 and C2, right? Again, this is comforting because, you know, we don't think friction should make the motion go unbounded in large time. Now there's case 3. Oh, I guess I should tell you the name of this. This very special case is called critical damping. Critical damping, all right? And then, or is that over damping? That's nothing is critical damping. Yeah. Oh man, I've got b equal to beta in my notes. What's up with that? Oh well, it is what it is. I'm sure I had a reason for doing that. Wait, did I do that? Oh, please tell me I didn't do that. Ah, I'm an idiot. This is so bad. This is very bad. I can't believe some of you didn't say something already. This is, what did I just write? Yeah, this is over. This is over damping. Under damping is case 3. I'm sorry, guys. My bad. The names do make sense. I'll talk about it in a second here. So what if we had b squared minus 4mk less than 0? Less than 0. In this case, we have lambda equals to minus b plus or minus the square root of, well, we could write this as, let's see here, minus 4mk minus b squared, right? If I did that, notice that 4mk minus b squared is what? That is positive. Okay? So one more step. This is minus b plus or minus I times the square root of 4mk minus b squared over 2m. So if I set this equal to like alpha plus or minus I beta, don't look at my notes. In my notes I put the b as beta, but I don't like that because I mean I'd rather save the beta and the alpha for my use of the characteristic. I've been doing that all this semester. I'm going to stick with that notation, yeah. So here, the real part is minus b over 2m. The imaginary part is this square root of 4mk minus b squared over 2m. And what's my solution look like? X is equal to c1 e to the minus b over 2m t times the cosine of beta t plus c2 e to the minus b over 2m t times the sine of beta t. Or if you like, I could rewrite it this way. It's the amplitude times the sine of, I'll write it in gory detail, the square root of 4mk minus b squared, all divided by 2m times time, plus some phase angle. You could write it that way if you like. But that's not quite right because I'm missing something. What am I missing? Anytime you're reading a solution of mine and I've got something at the end of the formula where it seems like it should be at the start, that just means I forgot it. Not here though, of course. This is just for teaching. So e to the minus b over 2m. But better late than never, right? So that's important, that term. All right, so let me attempt a rough sketch of all three of these. So here is a graph of x versus t, x versus t, x versus t. So I can't really do a very good job distinguishing between the first two cases, but it might be something like this. I can't tell. When I look at these, I can't tell the difference. They are fundamentally different, the overdamping and the critical damping, but they're both kind of sort of like this. If you were to study these equations, I don't think you can get too many critical points. If you like set the derivative equal to 0, how many different points can you have where you have, you know, velocity 0 for these curves? Not too many. Like at most 1 or 2, I think. I haven't worked it out. That make a good question, actually. On the other hand, I forgot to label it, actual underdamping so if we draw the envelopes like this, so the envelope I'm drawing here, this is x equals to, you know, a e to the minus b over 2mt. So effectively that's the amplitude, and I'll draw the curve in blue this time. So the motion here and so forth and so on. All right, I'm just starting the motion at t equals to 0 for the sake of discussion, all right? That's actually kind of a typical word problem, right? You're given the initial velocity, the initial position, maybe some other information. Maybe you could be given directly the spring constant, the mass, and the coefficient of friction, then you can go from here. Yeah. So do you see why the name underdamping, critical damping, overdamping. So what's a physical example of a spring in oil? Do you know? What are shocks on your car? It's a big spring, and there's oil around the spring. Yeah. Yeah, that's why there's a can around the spring. That's where the oil is. I suppose eventually the oil runs out and the shocks get worse, right? That's most of my cars. I never replace shocks. I don't know what that's like, replacing shocks in a car. That seems like an absurd luxury to me. But you've seen cars like this on the highway, right? They go over a bump, and then they just keep and on and on. Like, those are not properly set up shocks. Or maybe they are. Maybe you just need a lot of time to dissipate the energy because you're on the New Jersey Turnpike or whatever. If you know, you know. There's like 100-mile stretches in Alabama where you cannot afford to drive in the slow lane because the potholes are just like, I don't know, they're just insane. So you literally have to drive in the fast lane whether you like it or not, because otherwise you're going to kill your car. But anyway, so I think that's the reason for the terminology here. Any questions? There's a fourth case, and arguably a fourth case, right? Because it looks so different. I guess technically speaking, perhaps it's a special case of 3. I don't really think of it that way, though. Case number 4 is an important case. Which is b equals to 0, okay? No friction. In that case, we just have mx prime prime plus kx equals to 0, which gives us, m lambda squared plus k equals to 0, which gives us lambda squared is minus k over m, which gives us lambda is plus or minus I squared of k over m. Right? And so your solution is just something like a times the cosine of the square root of k over m times t plus a phase angle, right? And this is simple harmonic oscillator, or simple harmonic motion, if you like. This is the only thing I've written on the board, which as time goes to infinity, we get motion that's not 0. Right? From an energy perspective, that makes sense, right? Because in a simple harmonic oscillator, there's no friction force. There's nothing for the energy to go away. Like, it's just, the energy is just bouncing back and forth between potential energy and kinetic energy there. And so you just have this, all right? Okay, so anyway, that's my spiel about this. Any questions? And we work some problems now, maybe, yeah? So. Oops. Oh, man. Well, rats, well. I said there was one other problem we can talk about, right? What's that other problem? Anybody know? Circuits, right. So if you look at the RLC circuit, the resistor, inductor, capacitor circuit, and you were to study such a thing, if you were to have a voltage source, let's call it E, and then you've got a resistor, a capacitor, and an inductor, R, C, L. I did those wrong. It's RLC. I don't know for why is it RLC? I don't know. It just always is. If you do Kirchhoff's voltage law, you get E is equal to IR plus Q over C plus L di dt. So if you're in my physics course, you don't know about L di dt yet because that's like 2 weeks ahead. We'll get there soon, after that unpleasantness that's coming up Wednesday. Anyway, so Q, so I is dq dt in this context, all right? So in this way, we have r q prime prime plus, oh my bad, no, I'm an idiot. 1 over c, I'll get it eventually, guys. L q prime prime, that's the dIdt term, plus r q prime plus q over c equals to 0. So if you compare this with, m x prime prime plus, I'll get it eventually, b x prime plus kx equals to, now I didn't put this, but we could put a force over here, a literal external force on the mass, right? If I hadn't erased the picture, I could put a little dude and just had him pushing and pulling on the spring, right? An external force. Or perhaps you could put the spring vertically. The external force would just be gravity pulling down, which leads to actually kind of a boring situation. But anyway, we can have external force here, and I probably should put my external voltage here. And it's part of the reason that voltage is sometimes called electromotive force, partly because of this analogy. Even though the electric, like a voltage source here, is by no means a force, right? It does nevertheless force charge to go through the circuit, so yeah. But anyway, you see the analogy here. L is somehow like M, R is analogous to B, and 1 over C is apparently like the spring constant. So any mathematics that you can do for the spring mass problem, every theorem you can prove about the spring mass problem, there is a corresponding theorem for the RLC circuit. Right? So if I get rid of this and I just make an RLC circuit, which maybe initially has, the capacitor charged and some current flowing, so the capacitor is partially charged, the current's partially flowing, so that there's some energy in the inductor, there's some energy in the capacitor, and I let it free, what's going to happen is the current's going to eventually go to 0 because the resistor is going to dissipate all the energy. The resistor is essentially the friction force here, right? Energy is dissipated in the resistor just like friction force dissipates energy. On the other hand, there's some kind of way that energy is traded back and forth between the mass and the spring constant and the inductance and the reciprocal of the capacitance. But that's a rough analogy, right? You can kind of think of the mass in some sense stores energy in the kinetic energy. The inductor actually stores energy in the magnetic field. And then, the spring, well, it stores potential energy in the spring, whereas the capacitor, well, it stores energy in the electric field, although the relation's reciprocal, so the analogy it's not a direct one. Yeah. So, anyway. But I have found that this is very scary for students, so I don't test on this in here, but I do think it should be talked about. I know, but there's other engineers. There's other engineers. They don't feel as you do. I know, it's sad, but yes. Actually, did the non-electrical engineers have to take like a junior level electrical engineering course so that they're like more proficient in engineering than the general science educated population? That's weird. That's a that's a required course at NC State. I sat in that course for a day with my friend Somber Paul. In that one course, they covered like the entirety of what I learned in my community college education. That was a fast course. They had operational amplifiers, the whole thing. All the basic communication stuff was in there. Anyway, I digress. Let's work a problem. So I have, all right, I'm going to work one problem by hand here. So example 1, suppose we have that the mass, I like mass 1 kilogram, and we'll let the spring constant be 9, oh man, what's the units for spring I guess newtons per meter, right? Newtons per meter. And we'll put an external force equals to F naught sine of 3t, right? And at this point, my ability to care about units is waning. Yes?
Isn't the spring constant unitless?
No. Not in physics, but in here, yeah. Yeah, yeah. Yeah, the spring constant's unit. There's no units for mass. There's no units for spring constant. There we go. That's better. Thank you. That is how we roll in here. This is a math class. I don't know what units are. But whatever they are, let's say that we're implicitly working in units of newtons, kilograms, meters, and seconds. All right? Whatever those are. The most confused, I had a calculus 2 professor who was just, he had a PhD in topology. This guy was like really, really good at math. I mean, like, Dr. Lane was incredible. But the one time I saw him get confused is when he got lured into a discussion about British and English units in the section on like work. He's like, what's the units for mass? It's not pounds. What is, yeah, somebody was like, I think it's slugs. It's like, what? I've never heard of a slug before. What's going on here? You know, it's just because the whole English language and our British units are just physically inept. So you're set up for the fail in terms of the mass weight confusion. It's pretty much baked into the cake of the English language. But thanks, Britton. Anyway, so sorry. Oh no, think of the comments. And I buried it far enough, no one's going to notice. So let's solve this problem. And we'll assume that x of 0 is 1 and x prime of 0 is 0. Right? So here's an initial value problem with a forcing function. Let's work it out. How's it go? So the problem we're trying to solve here is x prime prime plus 9x equals to f naught sine of 3t. Now f naught here is a given but unknown constant that quantifies the force, the magnitude of the force, right? All right. So, okay, so great. So I've got lambda squared plus 9 equals to 0, which tells me lambda is plus or minus 3i. Therefore, my homogeneous solution looks like, you know, C1 cosine 3t plus C2 sine 3t, right? There's my homogeneous solution. Uh-oh, we're in trouble here, aren't we? Because the forcing function and the homogeneous solution, they're the same, right? They overlap. See that? This guy, in agreement, right? So the annihilator method suggests we make the particular solution to be what? Well, let's work it out. So we got d squared plus 9 times d squared plus 9 x equals d squared plus 9 on my forcing function. But of course, I just annihilated the equation, right? This is my annihilator. In this case, the annihilator is the same as the L, right? And so, lo and behold, this tells me that this would suggest that I have x equals to like what? C1 cos 3t plus C2 sine 3t plus C3t cos 3t plus C4 t sine 3t. Now, you don't have to, listen, this is all optional, okay? In the midst of this problem on the test, these are all optional. What's not optional, though, is that you start after this process or the process of remembrance, whatever it is, we must all agree that our particular solution should have the form t times a cosine 3t plus b sine 3t. Now, I say we must all agree, but admittedly, you could multiply the t through. You can switch the meaning of a and b. You can stupidly work in like C3 and C4 if you really want to. But that should be the form of the particular solution we use, right? I'm sharing with you the annihilator method as a means to understanding that this is the form of the particular solution because the other part's the homogeneous, right? That's what the annihilator method does for you, is it shows you need to multiply by t here. Then I calculate xp prime, and I get a cos 3t plus b sine 3t plus t times minus a sine 3t plus 3. I said it, but I didn't write it. There's a 3 here. And 3b cos 3t. Right? Clean it up. We've got, cosine 3t times a minus 3a. Oh, my bad. Not minus, but plus 3bt, right? Plus the sine of 3t. I got myself a b minus 3at. All right, great. Then xp prime prime, what's that? Well, we've got minus 3 sine 3t times a plus 3bt plus cosine 3t times 3b plus 3 cos 3t times b minus 3at plus the sine of 3t. Ha, came in handy. It's a good thing some random vandal installed these one day. Minus 3a, like that. Now let's rewrite that. xp prime prime is really what? So if we look at it, I've got a minus 9 times t times a cosine 3t plus b sine 3t. I've got that term. Listen, I knew that was going to happen, so I'm just showing you where this term and this term and this term and this term, those guys go together to give me all this. What's left is 3b cos 3t. Oh, my bad. Let me. If I could do math, that's a 6. Right, there's 6 of those. So 6b cosine 3t. That's from this and this. And I think I've got a minus 6a sine 3t. That is coming from the other terms. So this guy is coming from this one and that one, and that's everything. But let's just take a second to rewrite. What's the first term actually? This is minus 9xp. See that? So when I plug in xp prime prime plus 9xp equal to what? Well, it's equal to 6b cosine 3t minus 6a sine 3t. But what else is it equal to? It's equal to the given external force, right? F naught sine 3t. And so you see how the terms with time end up canceling out like that? That has to happen. If you've created your particular solution correctly, this must happen. All right, so then apparently, equating coefficients, we've got b equals to 0, and a is equal to minus f naught over 6. So my solution, in general, has the form x of t equals to c1 cos 3t plus c2 sine 3t minus f naught over 6 t f naught over 6 times t cosine 3t. Right? Now we're not done yet because we have initial conditions, right? What is x of 0 equal to? X of 0 is 1, but what else is it equal to? Yeah, C1. So it's equal to C1. So x of 0 is equal to 1, but it's also equal to C1 because you notice when you plug in time 0, sine of 0, 0, and this gives me 0. So C1 is 1. X prime of t is a little bit more complicated. It's 3 minus 3c1 sine 3t, right? Plus 3c2 cosine 3t. And then minus f naught over 6 cosine 3t minus f naught t over 6 times 3 sine 3t. And to be careful, I should have a plus here. Not that it matters, because when we plug in 0, what happens? That's 0, but we get a 3c2 here minus f naught over 6, yeah? And that's equal to 0, so therefore this time c2 is actually f naught over 18. And so in total, my solution is this. X of t is equal to cosine 3t plus f naught over 18 sine 3t minus f naught over 6 t times the cosine of 3t. What happens as time goes to infinity for this solution here? It goes to infinity. Why is that? What's happening? Yeah, agreed. The solution is unbounded. As time goes to infinity, you've got this t times cosine, which just keeps oscillating bigger and bigger and bigger, right? Now, physically speaking, the spring is going to break, right? Why did this happen? What's going on?
Is it because the initial force is being applied?
Well, what if the initial force is always constantly applied? I mean, that should alone not do it. I mean, we can talk about this situation here. You know, F naught, the external force here, yeah. You know, I've got K and M. Well, yeah, there's no damping. This doesn't have to happen, though, you see? The only reason this happened is because the frequency of the applied force and the frequency of the homogeneous solution was the same. You see that? The omega external was equal to 1, and that is equal to the square root of k over m. This is the so-called natural frequency of the system. So next time, what I'll ask is a more difficult question. I'll ask, if you have a spring and a mass in oil, right, and you're putting an external force like we just looked at on it, what happens? Like, what choice of frequency will maximize the steady state solution? So which gives you the strongest coupling? This is pure resonance. Pure resonance. This is what you don't want to happen, like if you're building a bridge, right? You don't want the wind frequency to resonate with like your bridge's natural frequency. Then the bridge will keep taking energy from the wind without bound, and eventually it breaks and dogs die. But anyway.